Now, we have to introduce the second law of thermodynamics. The second law of thermodynamics will be used in conjunction with our first law. And the second law of thermodynamics places restrictions on heat engines, refrigerators, and heat pumps, i.e. in terms of their maximum attainable performance. It also places restrictions on processes by governing the direction of heat transfer. The second law is very useful, for it guides the direction of all processes. It also allows us to determine the final equilibrium state for spontaneous processes, i.e. rapid expansion of gases or combustion. It also establishes a criteria for ideal performance, that is, our maximum theoretical attainable performance. And it allows us to quantitatively evaluate the factors that preclude the attainment of our best theoretical performance, i.e. irreversibilities. The second law is comprised of two statements. The first statement is the Kelvin-Planck statement, which says it is impossible to construct a device that will operate in a cycle and produce no other effect than the raising of weight and the exchange of heat with a single reservoir. That is, we cannot have a cycle that produces work when it is only exchanging heat with a single temperature reservoir. For instance, the Kelvin-Planck statement is shown below, where we have a high temperature reservoir providing QH to a heat engine which is producing work. Now, if we evaluated the efficiency of this engine, our thermal efficiency would be our power output per our heat input, and our power output would simply be QH. Thus, our efficiency would be equal to unity, or 100%. This is not possible, for our heat engine has to operate between two temperature reservoirs. The Kelvin-Planck statement implies that the thermal efficiency of any heat engine cannot exceed or be equal to 100%. The second statement is the Clausius statement, which says it is impossible to construct a device that operates in a cycle and produces no other effect than the transfer of heat from a cooler body to a warmer body. This is illustrated in the figure below. If we have a refrigerator or a heat pump, we cannot transfer heat from our low temperature reservoir to our high temperature reservoir without work. This implies our coefficient of performance beta, or beta prime, has to be less than infinity. You can think of this practically. Your refrigerator will not cool down items within the refrigerated space until you plug in the refrigerator to an electrical outlet. Both our Kelvin-Planck and Clausius statements are negative. They cannot be proven directly, rather only observed. And for nearly 150 to 200 years, these statements have not been violated, and they will never be violated. The equivalence of the statement means the truth of one implies the truth of the other, or proving one wrong implies the other is wrong. These two statements comprise the basis of our second law of thermodynamics. And these two statements rule out perpetual motion machines. Perpetual motion machines, PMMs, can be broken down into three categories. A perpetual motion machine of the first kind would create work from nothing, or it would create mass or energy from nothing. This violates our first law of thermodynamics as well as our continuity equation. Mass and energy can neither be created nor destroyed. A perpetual motion machine of the second kind is one where you'd have 100% efficient conversion of heat to work, or other forms of energy. And this violates our Kelvin-Planck statement. During any heat transfer process, there is going to be some irreversibility introduced, and thus you cannot have 100% conversion of heat to work. And a perpetual motion machine of the third kind is one that has no friction, where it can run indefinitely yet produces work. And this has been thought of conceptually, i.e. a frictionless pendulum in a vacuum. However, this device will eventually stop moving, i.e. it will not swing indefinitely. Now, let us look at an example of applying our Kelvin-Planck and Clausius statements. Say we have a high temperature reservoir TH that is supplying QH to a heat engine, and our heat engine is rejecting QL to our low temperature reservoir. From our low temperature reservoir, we are pulling QL into a refrigerator and rejecting a quantity QL to our high temperature reservoir. The work out of our heat engine, W dot, is equal to QH dot minus QL dot. And our work supplied to our refrigerator, W dot, is equal to 0. Now, does this device adhere to our Kelvin-Planck and Clausius statements? Although our heat engine does not violate our KP statement, that is, QH is greater than QL, thus our work out is going to be less than our heat into our system, and therefore we actually have a quantity, QL rejected to a low temperature reservoir, our Clausius statement is violated because there is heat transference from a low to high temperature reservoir without any work into a refrigerator.